This is the 10th installment of the Crash Course Regents Chemistry series, and this will be on nuclear chemistry. My focus, as always with these Crash Course Regents Chemistry series, is to get you ready for the Regents in chemistry or physical science chemistry. So my focus is what will get you the cover the material. Sometimes I go a little beyond that so you get a little bit of understanding, but my focus is that, so please allow me to do so. So let's get started. So a little background. These names are not anywhere near important. They're not necessary for the Regents, but just very quickly, Henry Becquerel was one of the first people to discover that materials had some kind of invisible energy given off that would expose plates that had photographic paper on it. And from his work, the Curies, through pitchblende and some other work, were able to identify certain elements that were radioactive. In fact, the Curie, Madame Curie, coined the word radioactivity. Okay, and this radio piece is that some of the emission by these metals that were invisible were due to not radio waves, but something like radio waves that have wavelengths, electromagnetic radiation, which we later found and coined to be gamma radiation, having no mass and no charge, except their wavelengths are much, much smaller, highly dangerous. The Curies didn't know how dangerous this was. Okay. Any case, moving forward, the Curies actually were able to identify individual elements that were radioactive or had this invisible energy emitting from them. It was, however, Ernest Rutherford. He was the person who actually started identifying what these emissions might be. They weren't really invisible, although there was, of course, emission of electromagnetic radiation in the form of gamma radiation that we'll talk about here. But he first discovered alpha radiation and beta radiation, which you've heard in your class. And the reason why it's alpha and beta is because, well, he found alpha radiation first, so he used the A for the Greek alphabet, and he found beta second. So that's a little bit of the background to where this is going. Now I'm going to move toward the presentation that I made for my class, and it's on the Crash Course site that I have. So if you want to run through it yourselves to a little review, you can, but I'm going to go through it to give you my presentation as opposed to trying to draw many of these types of equations. All right, so I'm in my website, and I'm in my review section, which is linked for most of my videos on the bottom, okay? And I'm in Crash Course 10, and I have this presentation that I put together, and it's clickable as if I was presenting it in class. So radioactivity, we just talked about the background, and before we can talk about the background, with radioactivity, it's very important you understand the concept of isotopes, because there are some isotopes of elements which you've already learned. Isotopes, again, are the same element, different number of neutrons. For instance, okay, hydrogen, this is hydrogen 1, hydrogen with 1 proton, no neutrons. So it'll look like this, 1 over 1. Why? Because a mass of 1 proton. There it is. Okay, now deuterium is hydrogen 2. Also hydrogen because of the 1 proton. But this 2 minus 1, the mass number minus the proton number, gives me 1 neutron. And then we have tritium, made famous for the Spider-Man movies, but this tritium is hydrogen 3. Why do they call it 3? The mass of 3. So these are isotopes of hydrogen. Now, unfortunately, one of these is radioactive, and the one that is called a radioisotope. And you're going to see a table called Table N called a selected radioisotopes. That really means, guys, that there are isotopes of elements that are unstable. Now, when I say unstable, I mean the nucleus is unstable. Okay, and we call it a radioisotope because this form of hydrogen, okay, is radioactive, meaning it's going to have some form of that invisible energy emitted, okay, and the reason why it does so is because it's unstable. Somehow, when it was made, okay, either artificially or through nature generally, okay, there's something that destabilizes the nucleus, makes it be high energy. One of the major concepts people don't have in nuclear chemistry, they don't understand that the reason why things are radioactive is because the nuclei, the nucleus of the atom, is unstable. We're not considering any electrons here. There is no electrons to talk about in nuclear chemistry. We're considering only the nucleus. And there's something in the nucleus that's very special. It's called the strong force. And in part, and I'm keeping this as simple as possible, the strong force is what keeps protons together. Now, interesting enough, we only have one proton here, so it's not a great example. But the strong force in nature generally keeps the nucleus together. And when you have a nucleus other than hydrogen, you have multiple protons. Those protons want to fly apart. They're positively charged, and like charges repel. So how do protons, which we've learned from the Rutherford's gold foil experiment, stick together in a very small space in the entire nucleus? Well, this strong force, this binding energy, keeps together. And changes in this strong force give tremendous changes energies overall. So we're going to talk about reactions at the end of this lecture that give up a heck of a lot more energy than conventional reactions with electrons. Electrons are from electrostatic charges, which are weaker forces. Believe it or not, the strongest force in nature is the strong force. So you start changing those changes, you'll have huge changes of energy in reactions. So I want you to understand, nuclear reactions deal with the nucleus because the nucleus is unstable. This one proton is stable. One proton, one neutron, stable. But this one's got too many neutrons. For whatever reason, too many neutrons, okay, makes this nucleus want to do something to relieve that energy. We'll talk about that. Now, getting back to some basics here. Isotopes, some of them are going to be radioactive. We call them radioisotopes. And notice something, these are all hydrogen, but notice their abundances in nature are different. We've talked about the weighted mass problem. For instance, carbon-12 and carbon-14. Carbon-14 is a radioisotope where carbon-12 isn't. Well, you can count the H's here. Carbon-12 is atomic number 6. 6 protons, 6 neutrons, mass number of 12. Carbon-14 is 6 protons. It better be 6 because carbon is identified by 6. But now it has 8 neutrons. So in nature, when it was made naturally, it has 2 more neutrons. And having too many neutrons, and the earlier elements like to have a 1-to-1 ratio of protons to neutrons, makes the nucleus unstable for some reason that we quite don't know. But we do know that it wants to change itself. And how does it change itself? In this example, carbon-14 emits a beta particle to become nitrogen-14. If you look with me, 14 minus 6 is 8 neutrons to 6 protons. When it emits a beta particle and changes its nucleus to become stable, now it has 7 protons and 14 neutrons. We call this transmutation. The atom changed because the proton number changed. We're going to get to how this works in a second, but I want to review the weighted mass problem because it pops up so much in chemistry. So I got carbon-12, 99.99% of the time. Most of carbon-12 is. All right, carbon-14 exists a very small amount of time. So to do the weighted average, you take the mass number, times it by the percentage, you get a number, take the mass number, times it by the relative abundance percentage in nature, okay, find that number, add it together, and that's why we get a decimal point in our reference table. We've talked about this at length, but I'm just reviewing that. Isotopes, weighted mass problems. Let's continue our discussion now. All right, so carbon-14 is radioactive and changing to a more stable nitrogen. Why is nitrogen stable? It has a nice 1-to-1 ratio of neutrons to protons. Okay, moving forward. Okay, so we talk about the proton to neutron ratio, but there's another problem with nuclei that you have to know. We know that atoms have tremendous amount of protons as they get bigger, and there comes a limit to how many protons can exist in a nucleus. All right, and we found out that anytime we have more than 83 protons in our nucleus, the nucleus just cannot hold those protons together, and that makes them give off some type of radiation or particle that changes their nucleus to become stable. So the first type of instability of the nucleus is too many neutrons. The second one is too many protons. And you should know there are no stable isotopes for any element beyond atomic number 83. That means there is no selective isotopes for anything with atomic number 84, 85. All of their isotopes are unstable. So there's no stable isotopes for anything with more than 83 protons. Okay? Now, talking about this ratio of neutrons to protons, early on when you have light nuclei, it's a 1-to-1 ratio. Here's your neutrons, here's your protons. Now what happens, party people, is that As you add more protons, you need more and more neutrons. It's called the stability zone. Okay, and early on, the protons equal the neutrons if they're stable. After atomic number 83, okay, 83 will be over here, everything is unstable. So there's a stability zone graph that shows this 1-to-1 ratio. Now, in truth, the stability zone goes above this 1-to-1, becomes a steeper slope, but we're not expected to know that. You should know a 1-to-1 ratio is what you want for elements 1 through approximately 20. Okay. Overcrowding of the nucleus and the neutron to proton ratio destabilizes the nucleus, and therefore the nucleus wants to become stable by giving something off. Okay, so let's continue on our discussion. Now, this is essentially table O. All right, we're going to see table O in a second, and we have essentially 4 different types of particles or types of emissions that a nucleus will give off to become stable. The first one is alpha. And we should know this already because we've talked about this in unit atomic structure. Okay, an alpha particle has a mass of 2, okay, a mass of 4, sorry, and a charge of 2. It's the heaviest of all particles. Really, what it is 2 protons and 2 neutrons. It doesn't have much penetrating power because it's so gosh darn heavy. And an alpha particle is a helium nucleus. Okay. Now, a beta particle is a high-speed electron that comes out of the nucleus. Kind of a strange thing. How does an electron come out of the nucleus? We'll talk about how that happens. But, like all electrons, is a charge of -1. And its mass is considered to be 0, even though it does have some mass. It's 2,000 times lighter than a proton. Or in this case, 8,000 times lighter than an alpha particle. So its penetrating power, getting into the cells, is much higher. This is a dangerous particle to be around. Okay, alpha particles are not as dangerous. Our skin will basically stop this. Our soft tissues inside us will not, but our skin will. Beta particles will go through our skin, will penetrate our cells, and could mutate our DNA and make us very sick. Okay, gamma radiation, we should know, has no mass and no charge, and it has the greatest penetrating power. Okay, because it has no charge, no place for it to deflect toward or to or from, and because it's light, it's just energy. Okay, it takes a lot to stop gamma radiation, something you do not want to be around. Now, a positron is really a positive electron. Okay, and you denote these values here. It is the same. But let's go to table O to see that, and here is table O in all its glory. And notice the top number is the mass number, maybe, and the bottom number is the charge number. So alpha particle has a mass of 4/2. Beta particle is that electron, 0, -1. Gamma radiation, no mass and no charge. Okay? And neutrons and protons. Positron is no mass, even though we say that for a beta particle and a positron, they really have some mass, which is really tiny. And of course, it's a positively charged electron. I'll talk more about that. So those are the types of emission that are given off. Notice we could care less about the electrons. It's all about the particles of the nucleus. Okay, let's talk about beta decay. Okay, now beta decay is the second form of radiation that Rutherford discovered. And as you probably were thinking, how does a nucleus give off, okay, a electron? Well, what happens is a neutron, and this is always with elements that have too many neutrons. A neutron is given off. A neutron splits into a proton and an electron. You may say, well, whoa. So if you think with me for a second, I got carbon 12. Oops. Let's go do this again. I'm sorry. So if you have carbon 12, and let's write this in here. And you know that it has 6 protons, it's carbon. And we know that this is stable because the number of protons equal electrons. But if I have carbon 14, who has too many neutrons, destabilizes the nucleus for whatever reason, it's unstable, it has high energy. So what happens is a neutron, which is neutral, from table O, splits into a proton and an electron. How about that? Negative and a positive. So a neutron is neutral because it's made up of things called quarks, actually, okay, that split into the positive part and the negative part. And actually, to tell you the real truth, a neutrino, electron neutrino, is emitted as well. Oh, well, neutrinos are not part of this course. I'm going to stop talking about them. Don't worry about it. So a neutron splits into a proton and an electron. And this is the electron that's kicked out. That's the beta particle. And think with me, if I've got too many neutrons and I lower my neutron number and I increase my proton number, I'm going to improve my ratio. So this thing gives off a beta particle, 0 mass, that's what we put there, e to the -1, that's its -1 charge. Look what it becomes. And I'm writing something called a nuclear equation. And we have conservation of mass, conservation of charge on the bottom and conservation of mass on the top. Let's do the charge first. What number plus a -1 equals a 6? And of course that'd be a 7. What number plus 0 equals 14? I'm going to guess 14. So my friends in chemistry, you just made nitrogen because atomic number 7 is nitrogen, and I showed you this on the other page. And look at the ratio, 7 protons, 14 minus 7, and then 7 protons because the atomic number is 7, and 14 minus 7 is 7 neutrons. Okay, and that ratio improved. And that's how carbon-14 got stable. It emitted a beta particle. Okay, and here is a nice little description. Neutron splits in the proton, a beta particle, and there's that neutrino that I talked about. Don't worry about that. Okay? Now, this is just showing you exactly how the nucleus corrected itself. Don't worry about that. And if you look down here, I have strontium 9038. I have a beta particle. What's X? Well, 39 plus a -1 is 38. 90 plus 0 is 90. What is X? Atomic number 39, if you look on the periodic table, okay, is Y, yttrium. So what is X? Y. So this is yttrium, okay? My little funny. All right. I want to take you to some other place, though. I want to take you to this little link here to show you how the particles in table O differ. We talked about alpha particles, beta particles, and gamma radiation. Let's go there for a second. And here we are. And let's undergo the response to radiation to electrical fields. Maybe. Okay, let's start an alpha decay. And notice this positive, notice it's 4 particles, 2 protons, 2 neutrons. Notice it does what? It goes toward the negatives. Why? It's positively charged. Why is it positively charged? It's got 2 protons. Let's start the beta decay. I'm shooting some beta particles. Notice they deflect toward the positive field. So what I'm doing is I'm putting a beta emitter, something that has beta radiation because it has too many what? Neutrons, and it's going to the positive. Notice the beta particle is bending more because it's lighter, goes faster. The heavier, slower, they should show this slower, alpha particle, okay, does not, okay, bend as much, or shouldn't, because it's heavier. And then of course gamma decay or gamma radiation, notice the little squiggly lines, those are showing electromagnetic radiation waves. They're not affected by the fields because they have no what? No charge. Okay? Penetrating power, something people don't talk enough about. I lower some paper, so I'm emitting an alpha particle, a beta particle, and gamma radiation. I lower the paper stops the alpha particle. Okay? So it's not a dangerous form of radiation on the outside of our bodies. Now I lower some aluminum. Now in truth, there'd probably be several sheets of aluminum, but we'll stop the beta particle. And I lower some concrete, that'll eventually stop the gamma radiation. In truth, it's probably lead in reinforced concrete of several feet thick that will stop the gamma radiation. But the one that penetrates the farthest is the one that is the lightest and has no charge. Second lightest, heaviest. This is what you're supposed to know. Okay, let's look at beta decay. Okay, and let's continue. It's our electron that comes out. I'll show the equation, the one I just gave you, and there it is. Okay, let's look at alpha decay. Maybe. Uranium-238, notice is atomic number 92. Anything above 83, guess what? Has too many protons. So this thing has too many protons. So it emits something called an alpha particle, which is a helium nucleus. 2 neutrons, 2 protons. So uranium becomes and naturally transmutates to thorium to become helium. And there's the equation. Why does this give off an alpha particle? Because there's too many what? Protons. You can't stuff protons in a small space without them going haywire and creating too much instability, so the nucleus gives off alpha particles and it lowers its proton number, right? A helium nucleus, my friends in chemistry, is 2 protons. By the way, helium is made by alpha particles being emitted by radioactive elements picking up 2 electrons as it floats up through the Earth's cracks. Okay? Now, the alpha decay, a nuclear equation, again, it's not about electrons, it's the nucleus. Uranium-238, okay, gives off an alpha particle and becomes thorium. And you should notice that 4 plus 234 is 238, and 90 plus 2 equals 92. Conservation of charge in the bottom, conservation of mass. All the numbers on one side on top equal all the numbers on the top of the other side. And that's how we figure this out and write a nuclear equation. Gamma radiation gives off gamma electromagnetic radiation, but notice it doesn't change the nucleus because, well, electromagnetic radiation doesn't have any mass. It's not made of particles. So something that has high energy, it's unstable because of some sort of high energy, gives off that energy, and notice its numbers don't change because, again, gamma radiation has no mass and no charge, as labeled by Table O. And this is the type of electromagnetic radiation you probably learned in class. This is the spectrum. Okay, the visible spectrum has a wavelength of 0.5 times 10 negative 6. Gamma radiation, much, much smaller wavelengths, high frequency, high energy. Okay, and this is a radioactive series. Let's go on to positron because something also comes up. Now, a positron is a little different. It's something called antimatter, and it was discovered in the 50s. It was only, in theory, we had antimatter. I'm not going to get into the philosophy of antimatter. You don't have to know that, so let's keep this short to the point here. But why a positron is given off is because a proton splits into a neutron and a positive form of an electron. Now, why would it do that? Why would a proton split into a neutron and a positive? You think with me, a neutron plus a positively charged substance with very little matter should equal a proton. We've said in this course that a proton and a neutron have the same mass. A neutron is a 1 and a 0. A proton, or an H, that puts on the protons, this is a what? Is a 1, 1. So they have the same mass. But in truth, they have the mass of an electron plus that. But it doesn't matter. It kind of makes sense that a proton could split into something that's neutral and something that's almost as light as 0 and has a positive 1 charge. And this is what's kicked out of the nucleus. It's a positive form of an electron. Now, why would that happen? Why would you want to lower your proton and increase your N number? I told you before, one of the instabilities of the atom is having too many neutrons to protons, like the tritium atom, right? Tritium had 2 neutrons to 1 proton. But guess what? There's a scenario where you do not have enough neutrons. So if your neutron number is too low, okay, positrons are given. And that's the reason why it happens. But again, you don't have to know that by heart. This is the particle. It's labeled in Table O, and you use it accordingly. So in the case of I have carbon 10. Carbon 10, carbon's supposed to be carbon 12. Well, there's an isotope of carbon that has 2 less neutrons than it's supposed to. So it's radioactive. It gives off a positron to become boron. Notice 1 plus 5 is 6, and 10 plus 0 is 10. And look at the ratio. There are what? 10 minus 5. There's 5 what? 5 protons and 5 neutrons. This was what? 6 neutrons and 6 protons and 4 neutrons. Let me write this bigger. Carbon 6, or carbon 10 I should say, okay, that isotope is a radioisotope. Why? Not because it has too many protons, not because it has too many neutrons, it has 2 less neutrons. Carbon is normally carbon 12. So if it has 2 less neutrons, it wants to correct that. It wants to destabilize. Right now it's unstabilized. It wants to become stable, I should say. So it emits a positron as labeled by Table O. Now, what do you get? And this is a Regents question. What do you get here if you give off a positron? Sometimes they'll say, hey, if this undergoes some kind of radiation, finish the equation, and we can go somewhere to find out if it gives off a positron. That'd be Table N. So we're going to look at Table N a little later, but Table N gives me the types of emissions that radioisotopes give off. I'm not sure if carbon 10 is listed there, but let's pretend you went there, you found it was a positron. And guess what I'm going to put? What number plus a plus 1 is 6? You put a 5, conservation of charge. What number plus 0 is 10? Wow, that's 10. And atomic number 5, you go to your reference table, this is boron. Don't be one. Get this right. Okay? I'll just pause for the laughter. Okay, laughter's over, or you're just in disdain with me. Now, moving forward, okay? We just corrected for the number of what? Neutrons. 10 minus 5 is 5 neutrons. What? 5 protons. This one had what? 10 minus 6, 4 neutrons, 6 protons. We should have a 1-to-1 for the earlier elements. This was less than that. So all of our emissions that we give off, whether it's alpha, that's a helium nucleus, whether it's a beta particle, which is a high-speed electron, or a positron, okay? These are all given off because atoms are unstable for different reasons. Do you have to know these reasons for the regents? No. But by going through what I just went through, it is clear in your head that atoms have the wrong number of stuff, neutrons or protons, and it makes them unstable, so they emit these particles to get stable. That's a regents concept, important. Now, what I have here is called a decay series. Now, I have plutonium-239 here, and again, you could just access this right from my site, from the link, okay, and play this yourself. But I'm showing you plutonium-239 having too many protons undergoes alpha decay. What does it become? Uranium-235. Now, plutonium on the periodic table, okay, is atomic number what? 94. It gives off 2 protons and it becomes uranium. Uranium's 92. Uranium gives off an alpha particle. It becomes atomic number 80 what? 8, which is who? Which is thorium. So you can see what's happening here. Okay, now, sometimes they have the wrong number of what? Neutrons. A beta particle is given off. But eventually all of these guys decay by losing protons. Sometimes they undergo beta particle decay to correct for the neutrons number. But they all come down to lead. Everything decays to lead, and it stops there. So if you know if you find lead in the earth and you know how much uranium is there with the lead, you can age the earth because they know how long it takes for uranium to go through all of these steps to get to lead. In fact, we age the earth inorganically, non-living, through the ratio of uranium to lead-207. Believe it or not, that's a curriculum-based piece of knowledge you have to know. All right, moving forward. All right. So everything beyond atomic number 83 is too many protons. So once you decay backwards, okay, into lead, all right, eventually now you are stable. Okay, another way to look at the decay series. Eventually going to lead. All right, and then we have, if you want to go through these questions, which element has no stable isotope? Well, it's going to be polonium because polonium is way above atomic number 83, right? So polonium, which was discovered by Madame Curie, is atomic number 84. So my friends in chemistry, that's above 83, so it has no stable isotope, too many what? Protons. Which type of radiation, when passed directly between 2 electrical plates, would be deflected toward the positive plate? The one that's negative, the beta particle. In electrical field, which emanation is deflected toward the negative, the one that's positive, the alpha particle? If you don't know that, go to table O. Which particle is given off when P32 undergoes transmutation? I don't know that, but when you go to table N, and let's do that, and table N is right here, and notice it gives you the selected radioisotope, because not all isotopes of elements are radioactive, unless you are beyond atomic number 83. Half-life, how much time it takes for half of it to decay into something stable. The decay mode, B negative is a beta particle, B plus is a positron, and of course our alpha symbol. If you don't know that, table O shows you that. We're looking for P32 in our question, and look at that, it undergoes beta particle decay, just looking it up. And that's why the beta particle is the answer. Okay, and then we have some questions here revolving the X. I'll just do one and we'll move on. I got palladium 23492 becomes uranium 23492. What's X? Well, what number on top plus 234 equals 234? 0. Okay. What number plus 92 equals 91? A negative 1. So I got a 0 and a negative 1. If I go to table O, that matches a beta particle. And that's how you do a nuclear equation. Okay, if you have a problem with that, it's an easy skill. I have a separate lecture on just nuclear equations below this video. The rest of these you can do on your own. If you want more practice writing nuclear equations, like cobalt-60, what does it do? You look at table N and you would find that it gives, well, I guess I just went too fast, but uranium-238 undergoes alpha decay and becomes thorium. Click on it again, do the next one, K42, look on table N, it gives a beta particle. I can figure out that this is calcium-42. Again, 42 plus 0 is 42. 20 plus negative 1 is 19. You can click right through my website. You can click right through this presentation to watch the tutorial. I'm just going to click through these, and you can just go through at your leisure. And these are just very similar. What else is given off? Uranium-235 becomes thorium-231 by what? By emitting an alpha particle. And I just add the top and the bottoms equal each other. So let's continue on. The three types of decay that we really have, alpha, beta, and gamma, alpha, beta, and positron, even though gamma is part of it, are considered to be natural transmutation. And here is an example of all the three types of emissions that give off particles. Of course we have gamma radiation, which won't change. These are all transmutations. These are an example of transmutation. Mutation means change. And transmutation means that the nucleus of an atom is changing because of the particle. So radon-222 becomes polonium-218. Neon-19 becomes F-19. They do so because they emit these particles from the nucleus. Because of what? Too many neutrons, too less neutrons, too many protons, and they become stable. So this is called transmutation, but they differentiate or differ. Transmutation differs, by the word artificial and natural. And all of these represent natural transmutation. What makes it natural or natural is that by itself, all of these atoms are by themselves. They are not needing anything else to make this happen. They, when they were made during the Big Bang or some kind of other radioactive decay, give off a particle to become more stable. We can't rush this process. We can't slow it down. And how long it takes for something to decay into something stable, is we measured by a half-life. And we'll talk more about that a little later. So a half-life measures how long it takes for a substance to go from one form unstable to stable. So if I have 100 grams of carbon-14, how long does it take for it to decay so that 50 grams of carbon-14 is left? That means 50 grams out of the 100 became nitrogen. So half-life is the amount of time it takes for half of the substance to decay into something more stable. So that number, half-life, that you see in table N, given it right here, does not change. Carbon-14 is 5,715 years. The reason why it's used to date, things that are organic. It's got a long half-life, and carbon-14 decays with a beta into that nitrogen I kept showing you. This is milliseconds. Look how short this half-life is. So these half-lives are constant because it's up to the atoms to decay into something more stable. We don't control that. It's a very important concept. And because these are constant, when these guys by themselves decay, we call it natural. Artificial transmutation does not have one reactant by itself emitting particles. What's implied, because they always have two or more reactants, is that these things need each other to collide in order to make these nuclear equations occur. And collisions of particles so that the nucleus changes are not natural. Most of them are done with particle accelerators. And a particle accelerator is something we've had a lot of news lately, with the Brookhaven National Lab being a very important particle accelerator close to us for many years, and of course the Large Hadron Collider built on the France-Switzerland border, which has unleashed new data to support that the Higgs boson particle exists. I'm not going to get into that here, but what I will get into is particle accelerators are important because what they do is allow us to study the pieces of atoms. But what I'm getting at here is that in order for these guys to collide, we have to have a particular type of an experiment or machinery to put these together, and that's why it's artificial. You don't walk through a field of flowers and look at the nature and see a particle accelerator happening naturally. These things we build and we use for experiments. So anytime you see two reactants in the reactant phase for a nuclear equation, it's artificial. There's transmutation happening, nuclei are changing, but these guys have to collide. Now, how do they collide? Because believe it or not, you have to know, how do we do this? Well, we smash protons in the CERN collider, Large Hadron Collider. We smash gold ions, among many things, at the Brookhaven National Lab. So we smash things that are positive ions or protons, of course, being smaller. We have to accelerate things that have charges. A particle accelerator works by a very basic principle using electromagnets. Okay, we take basically electromagnets. They go in, a long track, and of course we use a concentric circle eventually because we want to turn these guys. But basically what we do is we put a charged particle, let's make it positive, and the computers will make the electromagnets behind it, or on the side of it, these electromagnets too. All right, that's a bad drawing. Bad Garotsky. Okay, so let's put some magnets that are sitting on the containers here. And what we do is the computer makes these positive so as to repel this positive, because like charges repel, and the computer makes the charges in front negative so as this particle goes forward. Now as it moves forward, okay, it changes these positives, okay, well it keeps these positives, but it makes this one positive, okay. So if I was to move this forward, this line, okay, let's say it moves to here now, these would all go positive, okay, and the ones in front would go negative. So this would go positive to repel, and as it goes forward, we'd switch them on and off to keep repelling this forward and keep these guys going negative in front to keep this guy from going forward, and that's how we accelerate them. So because we use electrostatic charges to actually move the particles have to have a charge. So you could see a question on the region, say which of the following cannot be used in a particle accelerator, which cannot be accelerated, and you would see that a neutron, okay, 0, mass of 1, from table O, cannot be accelerated because it does not have a charge. Atoms cannot be accelerated because you should know an atom, the protons equal the electrons. So only ions are charged, are moved forward and accelerated, okay, in a particle accelerator. And if you go through my my Google presentation here, you'll see all the things I have here in videos. I'm not going to go through that. And the smashing of the atoms, the Fermi accelerator, and all that good stuff if you want to get more details. But I'm staying with the Regents curriculum right now, okay? And these are all the movies you could watch that talk about all the different types of events particle accelerators are creating and the information we're getting from them. Okay, and there's a Large Hadron Collider and also some movies about them as well. Higgs boson. Again, now getting back to the Regents curriculum, we have natural transmutation. Notice what? One particle. Okay, there's one reactant. Artificial transmutation, there are two reactants. And that's how you can remember this. Very simple. Okay, so number 3, which equation represents a nuclear reaction that's an example of artificial transmutation? Well, which one has two reactants? It's just that simple. The rest are naturally decaying. These guys have to be collided. And that's how that works. Okay, Now we're going to get to something called a half-life problem. Now I'm not going to hold your hand and spend a lot of time here. If you want to spend more time with half-life problems, I have a lecture below this video on my webpage for review that goes into higher details. But I will give you this. Given a half-life problem, I tend to use a chart method with a zero line. People do things differently, maybe your teacher did, but this is how I want to do this. So I have 8 grams of a sample of cobalt-60 existed in 1990. Which year will the remaining amount of cobalt-60 example be 0.5? So we're starting with 8 grams and we're going to 0.5. I want to see how many halvings have occurred and done that. So here's what I do. First I look at table N. Table N tells me that there is a 5.26 year half-life. Okay, that's the amount of time for one half-life. Then I draw myself a zero timeline. 0 time, 0 half-life, 8 grams, 100% of my sample. In this case, the 100% of my sample is the 8 grams. Now I'm going to start halving down until I get 0.5. So when I do so, I keep going. And it took me 4 halvings. Half of 8 was 4, half of 4 is 2, half of 2 is 1, and of course half of 1 is 0.5. And they said when 0.5 grams is remaining, so 5 halvings. I like this zero timeline because it separates 0 half-life. Some people think this might be 1, 2, 3, 4, 5 halvings. The 0 half-life line is nice because it separates where you're actually counting from. So look what I did here. 0.5 grams, and I added each half-life. The half-life is the amount of time it takes for half of the substance to decay. So the first halving took 5.26 years. The second half-life, we just added 5.26. So you had 4 half-lives, and each one was 5.26, and it's always going to be whole numbers in this course. So 4 times 5.26 is 21 years. So 21 years transpired. If you start as in 1990, 21 plus 1990 gives me 2011. So I'm adding 21 years, and I get 2011. All right? And that's how that works. Now these questions can start either from the top or the bottom. This time they gave me how much I had initially, how much I had remaining, figured out the half-lives, and we found the total time. Let's look at a different example. Okay, number 6. What's the total number of hours required for potassium-42 to undergo 3 half-life periods? There's my zero timeline, and you may not need this, but I look at table N, and K42 is a 12.4 half-lives. So if it's undergoing 3 half-lives, and each half-life is 12.4, it's 3 times that. Nice, easy problem. So 37.2 hours is the answer. Okay, you probably don't need all of this to do that, but hey, it's me over teaching. All right, so let's go on to the next problem. Okay, a sample of a radioactive substance with an original mass of 16 was studied for 8 hours. When the study was completed, only 4 grams of the substance remained. What's the half-life? Now they want you to come up with the half-life. So I start with my zero timeline. I can't look at table N because in this question, I don't know what substance we have. And if they did tell me the substance, it wouldn't be listed in table N. So guess what? I'm going to halve down until I get to 4. First half-life is 8. Second halving is 4. So clearly I have 2 halvings. And if it occurred in 8 hours, and there were 2 half-lives, each halving took 4 hours. It is just that simple. Okay, last one I'm going to show you. A sample of iodine-131 has an original mass of 16. How much will remain after 24 days? Okay, go to table N. Half-life is 8. And start my zero timeline. I'm starting with 16. I want to go down after 24 days. Well, I can't just count half-lives. I know that in 24 days, okay, there is 3 halvings, isn't there? If each half-life is 8 days, isn't 24 divided by 8 equal 3? Yeah, so 3 halvings occurred. And there we go. So 3 halvings occurred, and it took me 24 days. And I went down to 2 grams. Now, I don't have to do that, but the bottom line is each halving was 8 days. There was 24 days. Okay, they want to know how much will remain after the 24 days or 3 halvings. 2 grams would remain. That's my answer. Okay, So, one more, why not? Number 3, a sample was found to contain 2.0 milligrams. It was found. I like this question because it's going backwards. Here they're telling me how much was found. Okay, so this time, I go to table N. There's my half-life for carbon-14. And we know that 2 half-lives have transpired because that's the time, and it's a total time. There's the half-life and total time. You're always going to have whole numbers. So the total time is 11,460, and the half-life is 5,730. 2 halvings have transpired. Now, what I'm going to do is start with my 2 milligrams, because that was what was found after 2 half-lives. And I'm going to double back up. We have going down, we double back up. And that's going to give me 8 grams. So we notice 2 halvings have occurred. I'm starting out here and I'm going back up to my 0 line. Don't stop here. A lot of people stop right here. Go to the 0 line. If you want more work on how to do these 3 questions I have done for you with a lecture. So you can watch that lecture. It's linked here or it's below if you want to do more practice. The 2 major reactions that is seemingly asked in every Regents, and that's the reaction of nuclear fission and fusion. So nuclear fission is the splitting of the atom. So if you take a slow-moving neutron and a big nucleus like uranium, it will be split into smaller fragments and into more neutrons that can find other reactants, and a chain reaction is very, very possible. Okay, so slow-moving neutron collides and makes small fragments. More neutrons can hit, and if you have something called a critical mass, you'll have enough uraniums here, or fissionable material, to undergo an uncontrollable chain reaction. That is what an atomic bomb is. So you have to be able to identify that a neutron plus a big nuclei like uranium, okay, you don't have to know which ones are actually fissionable. There's only 4. Okay, so a big nucleus plus big nucleus fissional material, too many neutrons plus too many protons and neutrons makes it unstable, but this neutron collides with this big atom and it splits into smaller fragments into more neutrons. So we're splitting the atom. Okay, very important that you just be able to recognize it. And it can be written many ways, but you're going to see a neutron being captured by uranium that's going to make smaller fragments and then more neutrons. Not always written this way, but that's how you identify it. Okay, so nuclear fission, of course, is the reaction that we dropped on the bombs on Nagasaki and Hiroshima. And also it's the reactions we use in a nuclear reactor. So combined, that you can make a controllable reaction. So nuclear fission is a controlled reaction here, okay? And it's used commercially to produce about 30% of all of our energy. So there's some positives, huge positives here with this reaction. Okay, and some of the advantages is no air pollution or greenhouse gases. We're not burning fossil fuels. We're creating pretty much clean energy from a very small amount of fuel. Tremendous amount of energy is released when we fission an atom. And that energy comes from the equation of E equals mc squared. Okay, let me hold on for a second. Albert Einstein first postulated 1905 that energy and mass are interconvertible. And he said that matter can be converted to energy. They were one and the same within the space-time continuum. Now this is the speed of light squared. The reason why I bring this up, because all nuclear reactions, all of them, okay, undergo a change of mass into energy. So a little bit of mass is actually lost, which is kind of funny for us because we've been saying all year conservation of mass in chemical reactions, but in nuclear reactions, especially nuclear fission, okay, when the atom is split, if you were to add up and compare all the mass of the reactants and all the products, there's a little bit of mass missing. That mass missing we call mass defect, and that missing mass is converted into energy. So all you need is a little bit of mass times the speed of light, which is a big number squared, and you're going to get a tremendous amount of energy from this reaction. How can I say it? Very exothermic. Nothing is more exothermic than nuclear reactions, especially fission and fusion. So you will see questions on the regions that talk about mass, okay, being converted into energy. And they'll go the other way with that. Okay, so the mass that's missing, that gets used up, which is part of the binding energy of the nucleus, is converted to energy that's released. That's the way it goes here. Nuclear reactions go from unstable to stable, and they go from a little bit of mass being eaten up to making energy. All right? So nuclear fission, the splitting of the atom, okay, when you add up all of these reactants and compare it to the mass of the products, there's that little missing mass. That little missing mass gets converted into a tremendous amount of energy, more so than any kind of chemical reaction. Let's go through the advantages again. No air pollution, large amount of energy from a small amount of fuel, and decreased dependence on fossil fuels. However, there are some big disadvantages. Because we're splitting the atom and not all of the uranium that we use for fuel is splittable, we're going to have some unreactive uranium unspent fuel along with the particles that get split that represent radioactive elements. So we're going to have some radioactive waste that's produced from these reactions that have half-lives that are tremendously long and very dangerous. And we have nowhere to put this material. In fact, currently, all of that waste has to be stored on site, and it's building up. And we have no real answers for what to do with this waste. Okay? And of course, the biggest one is the potential for a meltdown. We've seen these, that there was a 3-mile island accident on our own land, Chernobyl. Japan recently, a couple of years ago, okay, had an accident with a tsunami that cut the power to their cooling ability, and there was complete meltdowns of their cores, which is their reaction, and radiation, poisoning, hurt a lot of people and continues to be a problem. So there is some serious concerns about nuclear fission and its viability, okay, commercially. Yes, there's some good things we can get from it, but these are some big disadvantages. Nuclear fusion, however, offers some really tremendous alternatives once we learn how to quite do this. Now you have to understand something. That nuclear fusion, the word implies fusing together atoms. Okay, so small light nuclei are coming together to make usually helium. Now there's a couple different ways to write this, but you're going to see hydrogens, okay, combining in some kind of ratio to make helium. Light nuclei coming together. And the energy given off in this instance is upwards of 1,000 times about more so than fission. So there's tremendously more energy released in these exothermic reactions, and that must mean that there's more mass missing. Right. Take the mass of my reactants, mass of my products, and there's going to be a lot more mass missing, which means more energy given off. Okay, so we're fusing. Use the word fuse to help you. These things come together. Okay, and of course, advantages of fusion, which is the energy that the star uses. Okay, can you not yell? So the important advantages of nuclear fusion is that there's an unlimited source of fuel. Fission, the splitting of the atom, we have to find fissionable material. Weapons grade uranium, uranium-235, is in small amounts. We do not have an unlimited supply of that. Okay, it takes a lot of effort to get enough to make fuel to run reactors and have bombs in the same fuel. But there's enough hydrogen and water, okay, to produce unlimited amounts of nuclear fusion. And it's clean. There's no pollutants. There's no radioactive waste that build up. And a glass of water can run Manhattan for many, many years, okay? And tremendous amount of energy produced more than fission because a lot more mass is missing converted to energy. The big disadvantage is that we haven't quite figured out how to do this economically. Right now it takes a lot more energy to start the fusion reaction, and that is because we're trying to combine atoms together. When you fuse atoms, you're trying trying to make nuclei, they're trying to make protons come in contact with other protons, and there's tremendous amount of repulsion that goes on there. So side by side, here's nuclear fission. Big nucleus with a neutron splitting apart, producing 3 more neutrons. Nuclear fusion, small nuclei coming together to make helium. Just helium, no other particles that may be radioactive. Light nuclei to helium, heavy nuclei splitting. Light nuclei fusing together that take tremendous amount of energy to start because you have protons coming into protons that repel each other. That's why it takes a lot of energy to start these reactions. Here we have a splitting of the atom. Okay, so you just have to be able to recognize these. Interesting to note that, notice the 3 here. I've watched some students get this wrong. Okay, when they're trying to find out what this particle is, and they'll go 90 plus 143, and they don't figure out what this is. This number 3 in front means you have 3 neutrons, so you have to 3 times 1, so this is really a total number. So you're trying to figure out, let's say, what this compound is, and you have 3, 1, and 0. You realize atomic mass of 3 here. So you know that this side has to equal 236, and this has to be 92. Okay, so to get 236 on this side, 143 plus 90 is 233, right? So you need 3 more. So you have to be careful when you're trying to write a nuclear equation and you've got 3 of these things here. Don't forget that that means you're going to have a total of 3. I've had people miss that. While we're on the topic, you can think of nuclear fission, the splitting of the atom, and fusion, fusing light nuclei, as artificial transmutation, right? You have to collide these two, and they just don't happen. Usually, these don't happen in nature. We have to create scenarios for this to happen.
With the uses of radioisotopes, and I'm not a big favor of this part of the chemistry curriculum because it's more of information and not understanding of concepts. So this is more like a living environment type of thing, but this is something that is part of the curriculum. So you should know that the uranium-235 to lead-206 ratio I showed you in today's crash course, that the decay series of radium-235 eventually goes to lead. So how much 235 uranium you have compared to lead can give us the age of the inorganic matter, like fossils and rocks, and actually the age of the Earth was done this way. Now, the ratio of carbon-14 to carbon-12 gives us the age of organic material. In fact, we can use carbon-14 as a tracer, meaning we can identify where it is in the body. If we were to put it into an organic system, we can see where it is over time to see how the uptake of carbon is done in a certain system. So carbon-14 is used as a tracer to see where things are. So these is how we date things that are non-living, things that are living, and we use the half-life periods to do so. Other important parts is you should know that we also use nuclear chemistry in human bodies to help identify where disorders or problems may be. One of the things that we use is iodine-131 for thyroid disorders, and thyroid uptakes iodine. In fact, we add iodine to salt, it's called iodized, so that we don't have malnutrition thyroids that used to give big goiters in the neck. So iodine-131 is used for thyroid disorders. Okay, technetium, and by the way, what we use in the body normally is something with short half-lives. When you have a short half-life, okay, that means it takes a very, very small amount of time for it to decay into something very, very stable. So these are safe for if they have shorter half-lives. Things that have longer half-lives are more dangerous, and unfortunately, when it comes to brain tumors and chemotherapy, radiation treatment, these technetium-99 is used to locate brain tumors, and cobalt-60 is used in chemotherapy. These guys in treatment and location of the brain tumors actually have very high and long half-lives, so they're dangerous. Of course they're dangerous. Chemotherapy is the idea that we're going to kill the cancer before we kill living tissue, which you have to be strong enough. So these are the ones they make you hold you accountable for. But the concept is short half-lives, okay, are definitely safer, okay, than long half-lives, and you should know why, because it takes a short amount of time for it to decay into something safe or stable. Okay, long half-lives are not something that we would pick to put into our bodies. And that, my friends, is essentially the entire unit, but I'd like to show you something from the New York State curriculum that's printed for your viewing pleasure. So this is right from New York State, what you have to know, just to show you that what I'm telling you is true. This is what you have to know. Explain the benefits and risks of radioactivity. Calculate the initial amount, fraction remaining, or the half-life of radioactive isotope given 2 or 3 variables, and we did that with our half-life problems. Compare and contrast fission and fusion reactions. We did that. Complete nuclear equations. Predict the missing particles from nuclear equations. I gave you plenty of examples of that. Okay, identify specific uses of common radioisotopes such as iodine-131 in diagnosing and treating thyroid disorders, and carbon-14 or carbon-12 ratio in dating once living organisms. Uranium-238 to Pallad-206 ratio in dating geological formations, and cobalt-60 in treating cancer. So these are the things we covered. And here are some other pieces from New York State curriculum. Each radioisotope has a specific mode and rate of decay. Nuclear reactions include natural and artificial transmutation, fission and fusion. Nuclear reactions can be represented by equations that include symbols which represent atomic nuclei with mass number and atomic number. Okay? And they can have emissions such as gamma radiation. Radioactive isotopes have many beneficial uses. Radioactive isotopes are used in medicine and industrial chemistry for radioactive dating, tracing, chemical, and biological processes. Nuclear power, detection, treatment of diseases. You know, one other use that I'm thinking about here is that I know a lot of restaurants now use a little bit of radiation to clean and kill microorganisms. So I'm just showing you how the things that I'm talking about, I'm getting directly, and I'm using the New York State curriculum guidelines here, the standards, so to speak, to answer this. So I hope you enjoyed that. That covers everything you need to know for the Regents. Please practice some questions. Okay, take care. Rock on.